In this video on directional properties of crystal, I want to talk about the connection between acoustic velocities and the elastic moduli. Well, the acoustic velocities depend on elastic moduli, and you can calculate velocities if you know the moduli, and they arise as solutions to a wave equation, which is based on Newton's law. In the case of general elasticity, a solution was found first by Christoffel, and a sketch of that derivation is given here. So we begin with Newton's law, which written in terms of stresses and displacements looks like this. On the left side we have a divergence of the stress, and on the right side we have the second derivative, the acceleration of the displacement multiplied by the density. Now we can substitute in for the stress the relationship from Hooke's law involving strain and elastic constants. And since strain is a function of the displacements as shown here, the combination of those, and one more item, we need to define a propagation direction for our sound wave in terms of direction cosines. So there's a vector S which has components in the x, y, z directions defined by L, M, and N. So just using those four ideas expressed in those four equations, the equation on the left can be separated into three separate equations. An acceleration equation for the displacement in the one direction, an acceleration in the two direction, an acceleration of displacement in the three direction. On the right hand side we have second derivatives of the displacement with respect to our propagation direction, and the linear term lambda, multiplying those derivatives, organizes itself into a 3x3 matrix. The lambdas contain linear combinations of elastic constants and direction cosines. The eigenvectors of lambda, since it's a 3x3 matrix, it has, in the general case, three eigenvectors, are equal to the density times the velocity squared. Eigenvectors of lambda define the polarization of the waves. I've provided a MATLAB function extol which calculates matrix elements of lambda and finds the eigenvalues and returns velocities and polarizations. So let's take an example. Collins and Brown in 1998 published a set of elastic constants for diopside, and here in symbols the circles are the actual measurements and the lines represent the calculations, and these are velocities in planes normal to the A star direction, the B direction, and the C crystallographic direction. On the left are the compressional velocities, and on the right are the shear wave velocities. Using the MATLAB function I provide, you'll be able to calculate these curves, and I'll show you an example there. This is a curve you could calculate easily based on the set of elastic constants published there, and I've just superimposed it on what we put in the publication. So here's a MATLAB script to accomplish this. First of all, we need to define what the elastic constants are, and I've written them in vector format. And the order of a constants is as shown there. First we go down the diagonal, and then we take care of the off diagonal, and then we take care of the uniquely monoclinic. There are a total of 13 elastic constants for this monoclinic crystal. Density has to be defined. Now here's a check that we've actually loaded our elastic constants correctly into the matrix for elastic constants. I just pass the vector, defining it as a monoclinic crystal, into make Cij, which returns a 6 by 6 matrix Cij. You can examine that matrix and make sure it has the form as we've shown previously. Now we need a set of directions of propagation, and I'm going to initialize a set of angles. In parentheses, I define a vector going from 0 to 180 degrees in steps of 2. The colons give the instruction to MATLAB of how to construct the vector. The prime after the parentheses says take a row vector and turn it into a column vector. It's the transpose operation. And I added 50 degrees to make it compatible with the illustration from the publication. Now I need propagation direction cosines, and here is a MATLAB command that will generate a matrix of direction cosines, each row being a propagation in one direction. So the trigonometric functions with a suffix of d means the argument going in is an angle in degrees rather than an angle in radians. So the first column is the sine of the angle, the second column is the cosine of the angles, and the third column is a bunch of zeros, and we have to define a vector that's the same length as our angles. So the command to give us our velocities is simply v is equal to xtil with arguments d cosine rho, our vector of elastic constants, and a flag that defines what symmetry those vector elastic constants pertain. We have the numbers, now we need to plot it, so let's make a figure. And this command sets up two side-by-side figures and plots to the first of the side-by-side figures. And simply plot the angles and the velocities found in the third column of the matrix of velocities. So the colon in this expression says take every element going down in the first index, which is the row index, and 3 is the third column over. So it's going straight down on the last column of our velocity matrix. Let's add some labels to the plot. Let's tell it what axes limits we want, angles from 50 to 230 and velocities from 7.3 to 8.6. Now that we've plotted compressional velocities, let's plot the shear wave velocities by plotting to the second of our side-by-side windows. Now here is the command that will plot the first two columns of the velocity matrix. So colon comma 1 to 2 gives us just the first two shear wave velocities. And again, we put in some labels. And we're done. Now there are other kinds of acoustic velocities useful for defining elastic constants, and I want to point out that one can work with surface or interfacial waves. And here is a crystal with a surface, and initially it is a undisturbed surface, so displacements at x and t equals 0 is 0. Now I'm going to apply a unit force to that surface, which will set up surface waves traveling on the surface and amplitude of displacements decaying with depth. Instead of the Christoffel equation that we worked with for the body waves, now we have displacements as a function of time and location going as Gij, which is the Green's tensor for surface waves. The Green's tensor is like the lambda tensor in the body wave problem. It contains information about the elastic constants and propagation directions. So analyzing surface waves involves solving for the Green's elastic tensor. Let me talk for a moment about impulsive stimulated light scattering, the sort of measurements we do in our laboratory. So we've been measuring elastic constants, equations of state, thermal conductivity, chemical activities in fluids, and structural relaxation using this method. And let me give you an outline of how that works. Well, it's a laser-induced ultrasonic technique. We're basically actively exciting acoustic waves and measuring their propagation. And we can work with both transparent and opaque materials. If it's an opaque material, we have to work with the surface waves or the interfacial waves if it's a sample in the diamond cell. And it's been used in diamond anvil experiments up to very high pressure. So there's a picture of a diamond cell sitting on our optics table with various lasers shining into it. And the idea is illustrated on the left with red rays representing infrared light coming in and green representing our probe signals. Let me take this to a little more detail here. We start in this experiment by shining infrared pulses that cross into the diamond cell. In their overlapped area, they establish an interference pattern which either thermally or electrostatically disturbs the material, setting up a perturbation in displacements which resolve itself nicely into elastic waves propagating in the plane of the sample. These elastic waves modulate, like a standing wave, modulate the local strain in the crystal, which perturbs the index of refraction, which gives us a grating off of which we can diffract. So a probe laser beam shining in transmits through the sample in a transmission body wave experiment, and some of the energy of the incoming probe is diffracted off of the grating caused by the acoustic waves in the sample. We put a detector in the path of the dashed green line and watch the time evolution of the diffraction grating. So on the left represents the easiest to understand example of a time domain signal in our experiments. This is time scale out to 40 nanoseconds. The laser hits the sample in this diagram somewhere around 8 nanoseconds, and then a single acoustic wave is oscillating as a standing wave in the probed area, giving rise to variations of the Bragg diffracted probe that show as in the diagram. It's a very clean decaying sine wave. You take the Fourier transform of that and it defines a nice frequency as shown in the inset. The acoustic grating, or the acoustic wavelength, is determined by the grating spacing of the overlapping lasers, which is well defined in terms of the angle of intersection and the wavelength of the laser. The velocity is given as the frequency times the acoustic wavelength. Let me show you time domain data for a crystal in a diamond cell at approximately half a megabar. The raw data is shown at top. It looks like almost like a sine wave that's slightly decaying, but in fact this single time domain signal can be deconvolved into contributions from a variety of acoustic waves in the diamond cell, and here they are. Starting at the bottom line is just the noise on that signal, and the noise level is extremely small. Then coming up the line, there's the diamond. An acoustic wave is excited in the diamond, and you can see its high frequency oscillation, since diamond has a very high acoustic velocity. Next up, with the largest amplitude, is the longitudinal elastic wave in the crystal that was in the diamond cell. Above that is a slower velocity associated with a compressional wave in the argon pressure medium. And then above that is yet a lower frequency wave associated with a wave propagating on the interface between the crystal and the argon pressure medium. The Fourier transform of the top time domain signal looks like this in the frequency domain. And you can see here in a frequency range from a gigahertz up to 8 gigahertz, we have a large peak associated with the longitudinal elastic wave in the crystal. We also see smaller peaks associated with both the longitudinal and transverse elastic waves in the diamond. There is the argon spike on there, which is the compressional wave in the argon, and then there's the larger wave, lowest frequency wave associated with a surface interfacial wave propagating between the crystal and the argon pressure medium. So in the single experiment, we've picked up measurements of the argon, a surface wave, and a compressional wave in this almost isotropic material. Here's a picture of the crystal that was used for those data. The scale of this photomicrograph is about 300 microns across, and this is looking at the tips of the diamond on axis with the diamond. There's a 40 micron on edge single crystal of ferropericlase in this experiment. There's a ruby pressure sensor, a small crystal of ruby, and the argon pressure medium is filling the space that has been drilled in this rhenium gasket. So this was a 6% iron ferropericlase sample. So one can measure acoustic velocities for waves propagating in the plane of the sample, in the plane of the diamond interface, by rotating the diamond cell about its axis. And so here we have a picture of a diamond cell with a diagrammatic sample between the two diamonds, and on axis one can rotate the diamond cell.